Well, good afternoon, everyone. This is our last day of class. Let's switch over for the spring 2023 semester, I should say. So if you're watching this in the future, that doesn't apply. That may not apply to you, but for spring 2023, this is our last day of class. We're going to finish doing the Math 13-14 final exam review today. We've already worked problems 1 through 17. We made 3 videos. We worked problems 1 through 5, and then 6 through 11, and then 12 through 17. And those videos are uploaded. Let's see. Click the link on the announcements that I posted back on January 19th. That'll pull up. There's our spring semester playlist for this class. And we'll go down and you'll see there's the first 3 videos where we're working out the final exam review. Up above it is the review for the 314 quiz. I noticed we only broke that into 2 parts. It was shorter. And as I said, if you're taking the test in class, next Monday, 5 days from today, from 2 to 4:30, 1 week from today, 2 to 4:30. So now we'll get started with the review, picking up where we left off. Here we are, the review for the Math 13-14 final exam. Oh, and when you click on that, if you're still working on the homework, I suppose surely we've mentioned this somewhere along the way. If you get this option and you're not through with the homework, you better say improved score. Don't say review and practice, because then you're not changing in your grade. So improved score, you're going to keep on working. And there are the 3 videos that I made last semester that where I was working out the review also. So if you don't want to bother with the spring 2023 playlist, you can access the review there. And I think we're ready to start working on logarithms. Oh, that is great. Oh, and let's see. Oh, and look what Jennifer brought us. But to celebrate the last day of the semester. Okay. The last day before finals start, I should say. And the classroom's practically empty. But and it's free, right, Jennifer?
No, it's $5 a piece. I gotta pay for next semester.
So there's free,
it's free with a tip. No, with a donation.
Yes. No, of course it's free. Okay. So we're going to continue this review. Number 8. Okay, not 8. Or 18. We're doing number 18. Let's put the problem back up. Tony, switch screens. Use properties of logarithms to expand. Expanding logarithms. That means you're going to take one logarithm and write it as multiple logarithms. So you're expanding it. So this says log base G of the square root of A. Notice only the A is under the square root times B cubed all over C to the 9. Okay, let me make sure
I didn't miscalculate. Is that why you got in the habit of putting the little thing?
Yeah. Yes.
Oh. That makes sense.
So make sure you can tell the stuff after it. That's why I put that little mark. Oh,
Ms. McGowan in the 8th grade.
Ms. McGowan in the 8th grade taught us, taught me, put that little mark at the end of the radical so you can tell, when it ends that this thing is not under that square root.
That makes sense now.
Okay, we had a trick. I said when we started exponential and logarithmic stuff, I said add this to your bag of tricks. If you see a radical in the problem, you need to rewrite it using a rational exponent. What exponent is equivalent to a square root?
It's a fraction.
It's a fraction. Remember we said, okay, right here, I'm going to remind you of something. The square root of a is the same thing as a to the 1/2. And in general, if it's a cube root or fourth root, the nth root of a is the same thing as a to the 1/n. So that square root of a we're going to write as a to the 1/2. And then we would look at the argument. That's the thing that follows the log notation. And we'd ask ourselves, how many distinct factors do we have on top?
2.
2. We have a times b. We have one distinct factor on the bottom, that's c. So that means we're going to need how many logarithms in our expansion?
3.
3, I agree. We'll have, let me write it down, log base g, log g, log g. The first one will have an argument of a. What are we going to do with the 1/2? Okay, put it in front, correct. Then, since b is still on top, are we going to have a plus or minus connecting these logarithms?
Plus.
I should, plus, okay. The argument is b. Where do we put the 3?
In front.
It becomes a coefficient in front, plus or minus.
1.
Minus, because we're moving down to the denominator, so a minus. The argument is a c. The 9 becomes,
9c.
okay. So,
Separate at multiplication and division, not at addition or subtraction.
That's the answer.
and there's the answer.
Put the little multiplication.
Those things are being multiplied. You separate at multiplication with the plus. You separate at division with the minus. And we saw when we first started this that every factor that's in the denominator, if there had been more than one factor, that other factor would have also been preceded by a minus, because that division there becomes a minus that distributes over every term that remains. Hopefully we have one where there's more than one factor in the denominator. Let's type in the answer.
1/2, right. Log. It's weird using a base G, isn't it?
I know.
Log base. Ooh, I want to type 9. G.
Get out of that subscript. A plus 3
Oops. 3.
log base G. Get out of that subscript. B minus 9 log base G of C. And check answer. Any questions there? Okay, the next one. Oh, it's another expansion. This is number 19. Use properties of logarithms to expand the logarithmic expression as much as possible. So we have the natural log ln of, I'm writing it down. We have an x to the, notice something when you're writing this problem down. That's 7. That's not saying a 7th root. If that 7 had wanted to be an index for the root, that 7 would have had to be right above this little hook. You see where my pointer is? The 7 isn't right above that hook. So what sort of a radical is this? We have an x to the 7th in front. What sort of radical is this? A square root, that's right. So we have x to the 7th and then a square root of
x squared plus 4 all over x plus 9. No, x plus 4 to the 9.
okay.
I like these LNs because you don't have to be typing that subscript. But make sure you're not typing a capital I. There's no time this semester you should ever type
a
a capital letter. Even when working with imaginary numbers, you better be typing lowercase I. Never capital I's. Never capital anything.
Well, I see a square root, so I know the first thing, just like what I did here, rewrite the radical using an exponent. So I have the natural log of x to the 7th times an x squared plus 4 to the 1/2 power, and we have an x plus 4 to the 9th power. A moment ago, Tony said you separate them at multiplication and division. You cannot separate at addition and subtraction. So that x squared plus 4 is going to have to stay an x squared plus 4. You can't split up that x squared plus 4. Likewise, you can't split up that x plus 4.
And that 1/2 came from the 2?
That 1/2 came, no, that 1/2 came from the square root is the same thing as an exponent of 1/2.
If it had been a
I was looking at the
cube root, it
letters
would be
and
a
a cube
1/3.
root.
getting
It
it
would
mixed up. Okay.
How
A
many?
just stands for any.
A stands for anything. The square root of anything is the
forget
same
that.
thing as a to the 1/2. Now, how many distinct factors do we have on top? I've already said x squared plus 4. That's one factor. You can't split it up. Do you have another factor up here on top?
I want to say 3.
No, I think it's right
Oh, it's
there.
gonna be
But
isn't
you're
it?
two.
saying 3 for all of them.
Oh, so you're saying there are 3 total? You're right about that.
Okay.
There's the x,
X to the
the
7.
x squared plus 4,
And
the x plus 9.
Yes.
So we're
X
going to
plus
need, the x plus 4. So we're going to need 3 logarithms. Ln, ln, ln. We start with the x to the 7th. The x is our argument. The 7 becomes the coefficient in front, plus or minus,
Plus.
plus because the x squared plus 4 is still on top, x squared plus 4. And notice, if your argument contains plus or minus, you're going to have to enclose it in that argument in parentheses. The argument is the thing after the logarithm. If you don't enclose it, they're going to count it wrong because then you're saying you're only taking the natural log of x squared. But you want to take the natural log of x squared plus 4. Do we have a coefficient here? If so, what is it?
1/2.
1/2 the exponent that was on the x squared plus 4, plus or minus.
Minus.
Oh, I'm running out of room. You see, so a minus. So here's my ln.
And then the X plus 4 to the 9.
X plus 4. Once again, if your argument, if it has a plus or a minus, you
9
got to
in front.
enclose it in parentheses. Where does the 9 go?
In front.
In
Right.
front. Correct. I need to write smaller.
Oh, you haven't written small all semester. Why start now? 7, and that's a good thing. People can see it easier. Ln, notice when I type the lowercase l and the lowercase n, it's going to space it and bold it.
There's the natural log function. Then he types the x plus 1/2 ln left parentheses x squared plus 4.
If you don't put the parentheses, it'll be wrong.
Because at that point, you're saying the argument of that second ln is just x squared.
The plus 4 is
Minus,
just an arbitrary piece.
minus 9 ln left parentheses, x plus 4, right parentheses. Any questions there?
I've noted myself when I'm doing homework that I'm looking at stuff and I'm getting ahead and writing things, and then I go back and I see it and I've already entered it and it counts it wrong, and I'm like, what did I do? And it's like I didn't put log in the right spot, or I didn't put the number in the right spot, put it in the wrong spot, and I'm having to catch myself very badly.
Oh, okay. You'll catch yourself on it. You won't do it on the final. Oh, number 20. This one looks shorter at least. Number 20. Express as a single logarithm, log base b of 7 plus log base b of, is that 11? 11. So we're condensing logarithms now.
We're going from 2 logarithms to just 1. That's what's single. So the formal name is condensing.
Switch.
Mm-hmm.
On 18 and 19, we were expanding. We started with 1 logarithm. We ended up with multiple logarithms. Started with 1, ended with multiple. Here, we're starting with 2 logarithms. We want to condense it down to 1 logarithm. So I'm going to write the log b notation. Log base b. I think the first thing we would ask ourselves at this point was, do we need a fraction bar?
No.
No, because
There is no denominator. There's no fraction.
there's no fraction. How do we know there's no? Here, that x plus 4 was in the denominator,
Right.
and it was preceded by what?
A minus.
A minus. So when you're going backwards, if you're going to have a fraction, you better have a minus connecting those logarithms.
Right.
You don't, so you can't divide. What's the only other thing you can do to arguments of logarithms? If you can't divide them, you must be able to, no. If they're being added, you multiply. So that's a 7 times 11. So the final answer, log base b of 77.
If this plus, the one that I have my cursor at, were a minus, the answer would have been 7 over 11. It would be a fraction. But here, because of the plus, there's no fraction. So do y'all see why we're multiplying the 7 and 11?
Yes, okay, type it in.
L-O-G space E. Now, since it's just a single number there, you can put the 77 in parentheses or not. Okay? I didn't type them, but it would have counted it right with the parentheses. Okay? Any questions?
Switch over here.
Okay.
And that's just what Tony was saying a moment ago. Suppose it had been log base b of 7 minus log base b of 11. That's when we would have written our log base b notation. And I would have asked, do we need a fraction bar here? And your answer would have been,
Yes.
yes, that minus there. You're either multiplying or dividing these things. If they're added, they're multiplied. If they're subtracted, you divide 7 divided by 11.
And that would have been it.
That would have been the answer. Okay, what else? Oh, number 21.
Listen. Over.
Oh, solve for t. I remember solving some exponential equations the last time, but we were able to get a common base on those.
So it was E equals E.
Right.
So here's what you do if there's not an e. And it doesn't say take the natural logarithm of each side, but it does talk about in decimal places.
If you use the common base, you can get exact values. That's the thing about being able to get a common base on both sides. If you get a common base, then you can get an exact value. You don't have to have something rounded. So what is that, a 0.06?
Yeah. Oh, yeah. Uh-huh. And a negative 0.89?
Yes.
Okay.
Switch over. Okay. We had said that if you're going to get a common base on both sides, you have to have, and you have a base of E on one, you have to have a base of E on the other. Well, we don't have an E over here, so our trick, we introduced logarithms on both sides. The one that I prefer to use would be ln, and that's going to really be nice because we know something about the natural exponential and the natural logarithmic function. They're inverse functions. When they're performed consecutively, what happens?
They cancel.
Okay. They're undoing each other, so it's like they're canceling, and you're left with just that negative 0.89t equals, and here you have that natural log of 0.06. We're trying to solve for t.
Divide by negative 0.89.
Okay, so divide by negative 0.89.
Negative 0.89.
So here's what you're going to have to punch into your calculator. It's a fraction. You have the natural log of 0.06 divided by a negative 0.89. If your calculator is like the one that we're using up here, when you press that ln, notice that it opened a parenthesis. So it opened up a parenthesis when you press that ln. So you better be sure to close the parenthesis once you type in that 0.06 divided by a negative 0.89. They ask us to round to 3 decimal places, so
I thought
that's
it said 4.
4
Did it say
decimal
4?
places. Yeah, I
Four
just saw
decimal
4 decimal places. Yes, so that's a 3.161. What's the fourth digit going to be? Is it going to stay a 1 or is it going to go to 2? It stays a 1. I agree. 3.1611. Any questions there?
Make sure you're closing those parentheses.
If your calculator opens them, that one, is that a TI? What is that? Jennifer, what are you using?
TI-30.
Okay, it's a TI-30X something or another. That's a really good calculator, okay? Yeah, I know. They're very, very
And I
affordable.
got it in one day off Amazon.
Wow.
That's why I
You
was
see
able to
that?
get so much done last
Hand
night.
that to me right now. Hand that to me right now, Tony. And
There's a couple of things on here that I was going to ask y'all how to. It looks like I have to shift, but I don't know how.
Oh, the second shift. They call it second.
Oh, okay.
Okay.
which one is it?
Oh,
And
some
it allows,
here.
I mean, it's direct entry, right?
Use this calculator and punch it in.
Okay, using this calculator here, sort of hard to see. You press LN, notice it's still open that parenthesis, so that's a, what is it, a 0.06, close the parenthesis, divided by negative 0.89, and 10, you get the same thing.
Mm-hmm.
And that was an $11 calculator.
That was
on
an
Amazon.
$11 calculator, that TI-30X2S, a very good direct entry, affordable calculator. Okay, of course, I guess we should have mentioned that at the beginning of the semester, rather than on the very
got it on the
last
last
day,
page.
after all the people went and spent $100 on these fancy calculators
Well, I hope they
that they didn't need. I hope y'all didn't do that. Number 22. Solve the following logarithmic equation. The common log of 5x plus 4
Wait.
minus, Tony, don't be playing with this computer, the common log of x minus 2 is equal to 1. Let's make sure I didn't miscopy anything. Okay, common log of 5x plus 4 minus the common log of x minus 2 equals 1. Okay. So let me push this get it right there. Here's a logarithmic equation. We saw a method we use when we're solving an exponential equation. We use logarithms. When we're solving logarithmic equations, we would use exponents, because exponentials and logarithmics are inverses of one another. When they're performed consecutively, they cancel each other out. So, looking at this one, to solve a logarithmic equation, our goal would be to get it in the form single log equals a number. We have two different logarithms here on the left side. We need to write that as just one logarithm. So we were condensing logarithms a moment ago. Let's condense these. Here's my log. Do I need a fraction bar? I'm writing two logarithms as one logarithm. Yes, because of the
Minus.
The black minus or the blue minus?
Black.
The black minus. This one right there. That minus says you're going to need a fraction bar. On top we have
5x plus
5x plus 4. And on the bottom we have
x minus 2.
x minus 2.
And on the side is minus 1.
No, I think we just
Am I
leave it
right
as
on that?
equal ones.
Oh, just
We-
equal 1?
Yes. Our goal, we want single logarithm equals a number. Single logarithm equals a number. That's our goal. What's the base of this logarithm?
10.
Okay, if you see log and there's no subscript, notice we had logs up there with no subscript. That's assumed to be a base of 10. And that's important because a log base 10, that can be canceled out by using an exponent base 10. Everything I have written here is about to become exponents. I'm going to raise both sides. Well, I'm going to make these both sides exponents to a base of 10. Remember when we were solving exponential equations the first time on with a common base, we'd say, oh, we have the same base, so we drop the base, set the exponents equal. Now we're going backwards. We have the exponents equal. Let's stick on the bases. Now, why do we do that? Because 10 to the log base 10, those are inverse functions. That's right, they disappear, leaving us just 5x plus 4 over x minus 2 equals, now what have we got on the right? It looks funny, but this is saying 10 to the first power. What's 10 to the first power?
10.
Just 10. Any questions there? Ten to the first power gave me just a 10. 10 to the log base 10, they disappear, leaving us, think of them as canceling each other out or undoing each other, leaving us just the 5x plus 4 over x minus 2. We have an equation containing a fraction. What do y'all think I'll do to solve this equation? I can think of,
Multiply x minus 2.
okay, so
Both
we're gonna cancel by multiplying both sides by the denominator. The other option is to treat that as 10 over 1 and cross multiply. If Kristen were here, that's what she likes to do when she has a fraction equals a integer. She puts it over 1 and cross multiplies. But Kristen took her final exam yesterday, so...
Now I know why she was saying bye yesterday.
Yeah, not yesterday, on Monday. Now I know why she was telling us bye on Monday. She was planning on taking her final and not coming by.
Heck out of Dodge.
Thanks a lot,
she
Kristen,
said.
for listening.
And I don't know what happened to Mary May. Where's Caitlin? Cancel the x minus 2's. That gives me, what have I got left on the left side?
10x negative 20.
Oh,
Okay,
yeah.
so that's on the right side, okay? So we have a 10x minus
sorry, I'm
20,
on the wrong
and on the
side.
left side we have
5x plus 4.
5x plus 4, I agree. And, you know, I like to move terms around in a way so that I decrease negatives and, within the terms. So I think what I'm going to do is I'm going to move that 5x over here. 10x minus 5x. What's that going to give me?
5x.
Okay. So I have a 5x here. What am I going to do with that minus 20?
Subtract 4. Or
It's a linear
Add 4.
equation, so you want to isolate x. So you'll add. I'm gonna add 20.
yeah, add 20 to the 4.
Okay. Add 20 to the 4 to give us what right here?
I have too much sugar in me. 24.
24. Divide both sides by 5 to give us x equals 24 over 5. And don't box that in yet.
Because if you look at the answer choices,
Reduce
it's possible that there's no solution. The solution is not a real number. You've got to sort of check your answer. Why do I say sort of check?
It's not that rigorous. It's not like the square root equations where there was so much involved in checking the answers. Here, all you have to do, you have to make sure that the argument of each logarithm is positive. So if you took 24 over 5 and plugged that in for x, 5 times 24 over 5, the 5's would cancel, so you'd have 24 plus 4. That's clearly positive. What about 24 fifths minus 2? That's what, 4.8? 4.8 minus 2, is that positive? Yes, so this number is an acceptable solution. Do y'all remember that? We have to make sure when solving a logarithmic equation, whatever number you get as a final answer, you need to make sure that the arguments turn out to be positive for it.
Usually, it's the negative. If you got a negative answer, you would mark it out.
That's usually the case,
And that
not
would be
always.
The unsolvable one.
Suppose we'd solved this equation and gotten
No solution.
1. Suppose we had solved this equation and gotten x equals 1.
That would be fine here.
5 times 1 plus 4, but what about this?
No.
No, 1 minus 2 is not positive. So usually if you get a negative answer, you have to discard it, but it's possible you could have a positive number that you have to discard. It's very rarely, though.
24 over 5.
Yes.
Are you ready for another one?
Any questions there before we go on to 23?
Oh, wait. I'm showing you blank sheet of paper.
Any questions there before we go on? Okay, let's do number 23 then.
Okay.
Log base 9 of x is equal to 1 minus log base 9 of x minus 8. Let me make sure that's a base 9, not a g, right?
Better not be a G. How
Yeah,
would you
you're
solve
right.
it
How
if it
would
was
you
a
do
G?
that? Yeah.
Mhm.
Those are 9?
Those are
It's a 9. It's a logarithmic equation, so just like the previous one, we need it in the form single logarithm equals a number. Well, I can get the equals a number on number 23 pretty quickly. To get equals a number, we're going to get equals a number. I could just move the second logarithm over to the left. Now, when I pick this logarithm up and move it over, that minus log base 9 is going to become, what are we going to do to get this 1 by itself? Add the log base 9 of x minus 8. This is the sign that changes, not the sign in the argument. So you have a log base 9 of, I don't know why I put that x in parentheses, plus log base 9 of x minus 8 is equal to 1. We need a single logarithm equals a number. What can we do to get, we want those two logarithms to be written as a single logarithm. So we're going to condense log base 9.
9 log.
Okay, we're going to combine them. Do I need a fraction bar? No. I'm not dividing, which means what am I going to have to do? Multiply. The logarithms are added, so you're going to multiply. Multiplying x times x minus 8, what is that going to give me?
I'm sorry?
Multiplying x times x minus 8, that gives me x squared minus 8. We're multiplying. Okay, maybe I better make a note here. You were taking the x times the x minus 8. So notice we distribute the x to get x squared minus 8x. And now we have it in the form single logarithm equals a number. What exponent base do we have to use to cancel out log base 9? I'm going to turn all of this stuff here into exponents. What will I put here to cancel out that log base 9?
9.
A 9. So 9 and 9. Everything up here, everything that's right there became became the powers with a base 9.
Okay.
Then 9 to the log base 9 cancels out, leaving us just an x squared
minus 8x.
on the left, and on the right we have 9 to the first power is 9. It's a shame they don't have something like a 2 there to make the point. It's not always just going to be that base. It just so happens the two problems we've done have been have had a power of 1 there. So 9 to the first became 9.
And
If that had been a 2, 9 squared, what would we have here?
A what? 2.
If that had been a 2, 9 squared would have become 81. It's now we have a quadratic equation. Whether we're going to solve by factoring or the quadratic formula, we need the thing set equal to 0. So there's only one sensible next step. What is it?
Bring the 9 over.
Bring the 9 over. I agree. That's going to give me an x squared minus 8x minus 9 equals 0. We're factoring a simple trinomial. A simple trinomial here and here. X squared, there's only one possibility. That's why this is called a simple trinomial. What times what equals x squared? X times x, I agree. What do we know about the signs inside the parentheses? That last sign's a minus.
There's going to be a plus and minus.
There'll be a plus and a minus. And then 9, there's two possibilities. 1 times 9 or 3 times 3. I agree.
It's going to be 1 times 3.
Okay, remember you choose the pair for a simple trinomial. You can look and choose the pair because you choose the pair that adds or subtracts to give you that middle number there. In this case, subtracts.
Minus.
Okay, so play around using 1 and 9 to get back a minus 8x. What should go here, the 1 or the 9? The x plus, I think Jennifer said it right the first time.
Oh.
Right here we have a 1.
Yeah, and then 9.
And there's the 9. Maybe we better check this. I'll seem uncertain. Or else you're just dreaming of summer vacation. So let's check.
And then I erased it and then said the wrong one.
First, x times x is x squared. Outer, what are we going to get? X times the negative 9. Negative 9x. Inner, positive 1 times x is positive x. And 1 times a negative 9 gives me? So is that giving us back x squared minus 8x minus 9? To the outer and inner, what is that? Negative 9x plus x. Isn't that a negative 8x? So it checks. But we're not through.
No. Then you're going to set to 0.
So coming back here, set those equal to 0. Set x plus 1 equal to 0. Set x minus 9 equal to 0.
So it's going to be negative 1, positive 9, positive 9 is to 1.
Okay, so solving, we get x equals negative 1. Here we get x equals positive 9. Are both of those answers acceptable? If you take negative 1, plug it in there with the x, you have a negative number after the logarithm. That is no good. If you plug it in here, negative 1 minus 8, it's still negative. That's no good. So negative 1 doesn't check. What about 9?
Yes.
Plug in 9. Is it positive? Yes, 9 is positive. What about here, 9 minus 8? Is that positive?
Yes, 1.
So,
like we said, it's usually the negative numbers you mark out.
for our final answer, just of 9. Any questions there? Find the determinant of the 3 by 3 matrix. This is number 24.
Crisscross.
Okay, so find the determinant. Let me write this down. Make sure I don't miscopy the problem.
I'm looking. 5, 6, negative 4, negative 2, 0, 0.
Let's make sure I didn't miscopy it. So there's 1, 5, 6. I had a student in my online class that was having a lot of trouble with the 3 by 3 determinant in the homework. Well, they did one problem. There were 2 3 by 3 determinants. They did one perfectly right and got the right answer. The other one, they just kept getting the wrong answer, and they didn't understand what they were doing wrong. And I kept replying back, do it just like the other problem, the problem right before there that you got right. And finally it became clear to me. look at this notation. This absolute value, you see they named A matrix. And notice they enclosed the matrix in those little brackets. You see the little bars there. Then she thought they were saying to take the absolute value. The determinant turned out to be negative. So she'd find the determinant, then she saw these bars right here that looked like absolute value bars to her. So she was taking, with something like her problem was ending up with an answer like negative 24. She kept typing in 24. And so this is not an absolute value. The funny thing is, you know why they use, if you took a linear algebra course, you discover that absolute values and determinants have a lot of the same properties. That's why we use those absolute value bars to represent determinants.
So these little bars here are saying determinant of A.
So they're getting you ready for the next
That would have been
steps.
just fine if it had not said anything.
Yeah,
or just use the DET abbreviation. I prefer that for determinants. Okay.
I just
really
prefer
haven't
to
even
switch
noticed.
over to mine, switch over to my paperwork. Here's what I prefer. Just enclose the matrix in the big absolute value bars. That's what it means for a determinant.
But you're not taking any absolute value.
There's no absolute values involved here. We had a trick. What was the trick? To see all of the cross products involved in this determinant.
At the first two rows to the left.
Okay, so those first two columns there, we'd write them back, we'd recopy them.
Oh. Negative in front of that purple too.
Oh, thank you. Is it little things like that? And then we're going to have parentheses minus parentheses. It's the difference of the cross products, but unlike with a 2 by 2 determinant where there's only two cross products, here there are three cross products falling from left to right, 1, 2, 3, and then three falling from right to left. So here we go. We start multiplying. Negative 1 times 6 times 0, that gives me 0. 9 times negative 4 times negative 2. Negative 4 times negative 2 is 8 times 9, that's a positive 72. What's the last product going to be? Falling from left to right. 5 times 0, a 0. Now we go in the opposite direction. We're still positioned at this 5. 5 times 6 times negative 2, negative 60, I agree. Negative 1 times negative 4 times 0. And 9 times 5 times 0. So that gives me the first set of parentheses, that's easy, it's just 72. Minus
Plus 60.
the second set of parentheses is a negative 60. And so Jennifer says that minus and negatives are got to become plus. So 72 plus 60, is that a 132? For my final answer. When it finally became clear to me what was causing that student's problem.
Oh, wow. I mean, I never thought of
Okay.
that. Okay.
She was taking the, I know it, she was using,
Very observant.
very observant. I think she maybe she knew a little more math than she needed to know at that point. So, oh.
Any questions? Let's try to find a 3 by 3 determinant. Any future physicists, you will do a lot of 3 by 3 determinants.
Mm-hmm.
Okay?
Mm-hmm. Okay, number 25. Oh, this is the last one we'll be doing this semester. Last problem on the review.
Says use Cramer's rule, and We have other methods you could use. When I glanced at it, my first thought was elimination, multiply the top by -3, but no, we'll do it with Cramer's rule.
2x plus 2y equals -3. 6x plus 8y equals 14. Make sure that it miscopy the problem. Okay. So, Cramer's claim to fame. Cramer did so much in the area of matrix theory, but this is the thing that he's remembered for, because it's taught in every algebra book in the world, I guess. The first thing he did, he formed the determinant of the coefficient matrix. So, and he called this D. D for determinant. He formed the coefficient. You have to make sure that the like variables are aligned and that the constant term's on the right-hand side. And that's what we have here. So, the like variables, the x and y, so we'd write the coefficients of x and the coefficients of y.
And then put the shoestring.
Okay, and then with a 2 by 2 determinant, you just multiply. 2 times 8 is 16, minus
12.
Multiply.
Make sure you're using that first number. Don't do 12 minus 16 on that previous one. Make sure you're using the first number when you get started. The first diagonal you should be doing is going downward when you look from left to
You
right.
start at that first number with the diagonals.
Don't start over here with a 5. You're going to get it wrong every time if you do.
16 minus 12, so our D value is 4. The determinant of the coefficient matrix is 4. Then, what Cramer did was he formed a new determinant called D sub x. D sub x is the determinant that you get if you realize this was the x column, that's the y column. He replaced that subscript says replace the y column,
The x column.
That subscript x says replace the x column with the column of constants. So we have a -3 and a 14. The x column is changed. The y column stays the same. You multiply. -3 times 8 is a -24. Minus, and realize that minus is part of the determinant formula. Okay? And then you multiply again. 2 times 14 is 28.
Oh, wait, there's. Oh, okay. 52? Sorry.
Yeah, I'm getting a -52. I was expecting it to be a 4 or a -4. So we found D sub x, and then he finds the determinant D sub y. D sub y is the determinant you get. You always go back to the D matrix. The x column is back to its original values, 2, 6. The y column is the one that you replace with that column of constants, -3 and 14. We multiply. That's a 28 minus multiply -18. Watch out those double negatives. Minus and negative becomes plus.
46.
So you have 28 plus 18. I agree with 46. And here's what Cramer was able to prove that gets him mentioned in all the algebra books. The value of x will always equal D sub x divided by D. d sub x was negative 52, divided by d, 4. Negative 52 divided by 4, is that a negative 13? So that says that these lines here are going to intersect with the next value of negative 13. That's what we're looking for. Solving a system of equations, we're finding where those graphs intersect. They're lines, so they're intersecting in one point with the next value of negative 13. The value of y, that's d sub y divided by d. D sub y was 46 divided by 4. Well, I don't think this is going to go in as nicely. I think we can cancel a 2 above and below. 46 divided by 2 gives me a 23. 4 divided by 2 gives me a. So the y coordinate at the point of intersection is it's 23 halves. So let me write it bigger.
Okay.
Negative 13, comma, 23 halves. That's what we're looking for.
Parentheses, negative 13, comma, 23 over 2, right arrow before I put the parentheses. Any questions there?
Okay.
Were there any problems in this where they had to find the vertex of a parabola? Is there any vertex of a parabola or axis of a parabola?
I don't think
Because sometimes I got some questions the other day from a student that wanted to know, well, do we write x equals here, like on this problem? Like on number 22, they give you the x equals. So for number 23, she thought, okay, I got to type in the x equal, got it wrong. There's no time you should be typing in the x equal unless it's one that says, find the axis of a parabola.
The equation of a vertical line. That's right.
And I don't think that there's any like that on this review, were there?
I don't recall.
So you shouldn't type in x equal.
That's one of the purposes of this review, is for you to make sure you know how to type in those answers.
Mm-hmm. Yeah.
Okay, I think we'll stop the recording.